Hi, my name is Ronnie, and in this module we'll look at a 10-step design guide for additive manufacturing. The agenda for this video is to first look at why we should design for additive manufacturing. Then we're going to go through a 10-step design guide to achieve the successful design, and finally we're going to round off with a few conclusions. So why should we design for additive manufacturing? Well, previously with subtractive manufacturing we used to remove material from a block, but now with additive manufacturing we have to add material in order to create something. So there's a shift in the mindset from removing material to adding material. When moving from subtractive to additive manufacturing, we get the most out of the technology if we actually design for it. In this pyramid we can see some of the different ways that we can use additive manufacturing. And ideally, we want to be on top of the pyramid where we utilize additive manufacturing to create new products. If we look at some of the benefits that we achieve by moving to the top of the pyramid and design new products, we can see that there's a whole range of them. We need less support material, we get a better surface quality, we get a lower price, shorter print times, better tolerances, and we're able to fit more parts on a platform. In addition, we get a range of design benefits, as we can see here. For instance, we can build lattice structures, we can make lightweight products, and we can take advantage of part consolidation. Now we're ready to start designing, and to best illustrate how you design for additive manufacturing, I've brought a case. Here we need to redesign a robot gripper for additive manufacturing. For this product we have a clearly defined requirement specification, and we also have some goals that we want to achieve. For instance, we want to make it lighter than 1300 grams, and we want it to consist of significantly fewer parts than the 72 we see here. So which of the design benefits that we saw before can we actually utilize when redesigning a robot gripper? Well, first of all, we can make it lighter, then we can make part consolidation so we end up with fewer parts in total, and we can integrate the air tubes for the suction cup into the gripper itself. So to go from the original gripper to a 3D printed gripper, we need to go through 10 design steps. First, we need to choose the material that we want to print in. We have to choose the technology that we want to use. Then we have to define the contact areas and define the print orientation. Then we have to connect the contact areas and add the support structure. Then we have to look at the cross-section area and pay attention to the different design rules. Then we have to validate the design, and finally we are ready to print. The first thing we need to do is to see if the material that we want to produce the gripper in is actually available. One place to start is this Zenvol database that lists all the different materials that you're able to print in, paired with the printers that you can actually print these materials on. I've decided that we want to print this gripper in aluminium since it has a good strength and it's lightweight. The next step is to choose the printing technology that we want to use. This overview is a good place to start, and below you can see the different materials that the technologies are able to print in. I've listed the ones that could be interesting for manufacturing a robot gripper, and the one marked in green is the one I decided on. When looking at the technologies, we need to clarify what the build volume of this technology is it sufficient, and do we need support material or not? What kind of post-processing is needed? What are the tolerances and could they be a challenge? What is the surface quality, and do we have any demands for surface quality? And finally, how can we quality assure our gripper? We've decided on the SLM technology, and I'm fortunate enough to have an SLM 280 metal 3D printer available. That's the one that you can see in the upper right corner on the picture. Below you can see the volume of the build chamber, and to the left you can see that there's different layer thicknesses available, which defines the quality that you get out of the printer. The standard is a 60 micron layer thickness. In addition, we can see that it uses two 700 watt lasers, which also affects the quality, but also the speed with which you can print. Now that we've selected the printer, we have to look at the contact areas. Basically, it's about connecting A to B in the easiest possible way, and usually there are some obstacles that you need to get around, here illustrated by the two stars. If we apply this to the robot gripper, we see the gripper here, And here we see the contact areas. We have the suction cups, then we have the mounting bolts to mount it on the robot, and finally we have a fitting for the pneumatic connection. So these are the contact areas that we need to connect in order to make a robot gripper. Now that we've defined the contact areas, we need to look at the print orientation. The orientation is very important, both because it gives some benefits if you have a good orientation and it impacts your design. When talking about orientation, the vertical direction, also known as the Z direction, is the most important. Some of the benefits of a good orientation could be that you reduce the need for support material, you improve the surface quality, and you get a shorter print time. If we apply the orientation to the robot gripper, then to the right we can see that I've defined the Z direction as the direction which the gripper is actually mounted on the robot. I've done this because I believe it will give us the most symmetrical robot gripper, but that might change in the design phase, where you learn something different through design iterations where a different orientation may make sense. But as a starting point, I want to use this orientation as the basis for my design. The first thing to do after defining the orientation is to draw different sketches of how you can connect the different contact areas. The blue lines show where we need some air flowing through tubes and also where we need some strength in order to lift the box that will actually be lifting with this robot gripper. In addition, we have the red lines, which is where I want to connect the gripper to the robot itself. Here we've made a sketch of the connection between the different contact areas, and now we can start to add some volume to these areas. It could look something like the drawing we see here, with round tubes connecting the contact areas. And we could actually just print it like this. But since we're printing with the SLM technology, we have to account for support material. So it could be interesting to see whether or not we could reduce the amount of support material. That is because it gives some significant benefits to reduce the support material. For instance, you reduce the print time, you reduce the support removal time, you reduce the amount of grinding needed to remove support marks, and in turn you get a better surface quality. One way to reduce the amount of support material is to optimize the angles so that they're all above 45 degrees in relation to the build platform. Another possibility is to reduce the build height and thereby also reduce the need for support material. You can optimize the shape of the channels so you don't need support inside the channels. And finally, you could build support as part of your part, as we see in the picture in the bottom right. If we look at support material for the robot gripper, I've added it to a preparation program where I've auto-generated the support to see where the support is and how much there is. If we start with figure A, this is the orientation I took as my starting point. And here we can see that there is some support material, so maybe it would be possible to reduce this. In figure B, I've turned the gripper upside down, and we can see that there's almost the same amount of support as in figure A. And in figure C, I've tried placing it vertically because that way we could have more grippers on one platform. So this could be an option if we wanted to series produce it. But I've decided to move forward with figure A because I think that gives us the best orientation. Now we'll look at the robot gripper again and see how we can optimize it using some of the guidelines that we saw earlier. One way was to reduce the height and thereby reduce the amount of support needed. We've tried doing that here, where we have reduced the height from 92 millimeters to 49 millimeters, and as we can see, this reduces the amount of support with nearly 50%. The next thing we need to look at is the shape of the channels where air will be flowing through. Our channels are designed with a diameter of 10 millimeters, and here we can see that it's not possible to design round channels with a diameter of above 8 millimeters without using support inside the channels. So instead, we need to choose one of the other 4 options for shaping our channels. So we can make it ellipse shaped, droplet shaped, diamond shaped, or shaped like a house. And these are the 4 options we have for shaping our channels, if we want to avoid support inside the channels. As we can see to the right, we can also combine these different geometries when designing the channels for 3D printing. I've decided to move forward with the figure that we see in the bottom left corner, where we combine the round geometry with the diamond-shaped geometry. Now we take this knowledge about channel design and apply it to our robot gripper. And then we end up with a design that could look something like this. Here we have the round holes in the vertical direction, and we have the diamond-shaped channels in the horizontal direction. Next, we need to look at how we can optimize the cross-section area of the printed part, since this has a huge impact on the quality that we end up with. Here's an example of a large block where we've defined a C direction. That means that we'll print a lot to begin with, but we'll also have some big leaps in the printing process in terms of how much we'll be printing in each layer. There's different ways of solving this issue of making the part more printable by optimizing the cross-section area. One way could be to orient the part differently. That way, as we can see in the graph, we get less that we need to print in each layer, and we get a more even increase in the amount that we need to print. That in turn gives us a better quality of the printed part. So the orientation definitely has something to say. Another way to optimize the cross-section area could be to add chamfers or roundings to our part. This doesn't really cost extra to print, but it significantly improves the quality of the printed part. A final way to optimize the cross-section area could be to hollow out the part and maybe, as we see here, add a honeycomb structure inside. This would also give us a lower volume to print in each layer and in turn give us a better quality of the final printed part. Let's make a quick analysis of how this looks for the robot gripper. If we look at the graph to the left, we can see where we have changes in cross-section area where we start printing more, and at the red arrow is where we potentially could have a challenge. If we then look at the picture to the right, we can see that the yellow lines indicate that there's a change in the cross-section area, and that's because we start printing the attachments. So here it's a good idea to have some roundings here below in order to allow for a smoother transition in the amount that is printed. In addition, we can see that the big changes are when we go from printing something to not printing anything. So we're not too worried about that. And we're not too worried about the green arrow either, since we're decreasing the amount that we're printing. It's more when we're increasing the amount that it could be a challenge. But the way the design of the gripper is looking now, I don't see any challenges in printing it. Now it's time to look at whether the robot gripper complies with the general design guidelines for the technology that we have chosen. For this, Hubs is a big help. They offer the 3D printing handbook, which is a great help when designing for additive manufacturing. But in addition, the table that you see to the left is very helpful. Here you have the overall measures and limitations that you need to stay within in order to get a successful print. If we proceed with the bottom one, which is for the SLM technology, which is the one that we're using on the robot gripper, we can see that there are some general measures and limitations that we need to stay within to ensure that we get a successful print. Here I have listed the ones that I find particularly interesting for the robot gripper, and these are the ones that I want to pay close attention to. We need to check that we don't have any wall thicknesses that are below 0.4 millimeters, and our smallest wall thickness is about 1 millimeter, so here we are quite safe. We already looked at support and overhangs, where we designed our channels so they didn't have overhangs that were outside the guidelines that we see here. The smallest holes that we have on the gripper is for the mounting bolts, and they have a diameter of 6.5 millimeters. So that's also well beyond the limit of 1.5 millimeters, so that shouldn't be a problem either. And the escape holes where we need to get our powder out have a diameter of 10 millimeters, so that's not a problem either. And finally, we can easily live with the tolerances of plus minus 0.1 millimeter. Consequently, we can see that the robot gripper complies with the general design guidelines for SLM. The final step before we start printing is to validate our design. We can check that the robot gripper actually fits on the robot, and we can do that in our CAD program. We can also use simulation tools to simulate if the robot gripper is strong enough and if it's possible to optimize it even more. If we look at the robot gripper, I've made an FEA simulation where I used a safety factor of 1.5. Here we get a maximum stress of 88 for the robot gripper, which is well beyond the yield stress. We also looked at the displacement when lifting a box of 4 kilos, which this gripper will do, and the maximum displacement was 0.3 millimeters, which is acceptable for a gripper of this type. This indicates that we could optimize our design even more, maybe by reducing the wall thicknesses of our channels from 1 millimeter to 0.4 millimeters. Now we're ready to start printing. We've managed the design phase. Now we need to convert our file to a printable file format. Then we need to add it to a preparation program where we orient our part the way we designed for. Then we add the support and we slice the build job into several layers, which we can then print. Then we start printing, and afterwards we remove the support and take the part through the necessary post-processing steps in order to get a nice surface finish. What we achieved with this case is that we reduced the number of parts from 72 to only 6 parts. We reduced the weight from 1300 grams to only 150 grams, which is a very big reduction. And finally, we integrated the external air tubes into the gripper itself. In the picture to the right, we can see what the gripper would look like when it's mounted on a universal robot. To sum up on design for additive manufacturing, this new manufacturing technology has given us a lot of new design possibilities that we can apply to our parts. Of course, there are also some restrictions for the different technologies that we should pay attention to. So the goal is to end up down here in the area of design freedom, where we utilize all the different design possibilities, but at the same time pay attention to the restrictions, so we end up with a great design for additive manufacturing. Finally, what we want to achieve when designing for additive manufacturing is to design some great parts that are also great when they come out of the 3D printer in the end.